Oh, I don't
So you
know.
don't have to prove.
Oh, well, it's very simple because you.
So it's obvious. It's obvious.
Obvious.
So it's not a theorem. Proposition.
Yes,
Okay.
I agree. Yes, indeed. Yes, indeed. Yeah, because you have to play with the micro flips, so it's not a big deal. It's not a big deal. Okay, now the purpose was to work out in the Q world if we have this kind of results. So in other words, find the statistics on doublets in such a way that this unique function, by that start, this unique function, you see, this unique function for interlaced doublets is equal to polynomial Q, which is a polynomial with positive integral coefficients. And, oh, that's written here. Okay, with PQ have positive integral coefficient, P to the 1 equal to 2 to the n. So a true Q analog of this. How can we work this out? So we had the proposition of Durand before, you see, this has to be expanded to the Q analog. And can we, does it exist? Or if we have introduced those doublets, they should be useful to something. Otherwise, it's useless. Okay. Those was motivated by the search for Q analog with the tangent number. Okay. So this is my second definition. I hope that you, okay. Okay, now the doublets, so we still have the doublets in mind. The interlaced, the normalized, we have the flip-flop, we have the microflips, that's all. That's all we have to remember. And we look for statistics of the doublets in such a way that the counting we had before could be expanded to a Q environment. Okay, so now let's start with the doublet like this. Okay, remember that we have this permutation, you fold it like this, and you have this reading. And now we are going to study the descents of the permutation, actually of this, of that row of delta. And let's suppose the descent occurs at I greater than I plus 1, or it may occur also at an greater than bn, or in bi minus 1 greater than bi. Oh, no, I'm wrong in here. It's bi, no, it's no good. Bi greater than bi minus 1. You see? Bi greater than bi minus 1 because we go backward. And suppose they occur at position L1, L2, and R, then we define the descent and the number of such descents, right? No problem. And there is also a statistic which has been introduced by McMillan. So the measure index of the doublet would be just L1 plus L2 plus LR. The match would be this. So this is very classical. It goes back to McMillan, to 100 years ago. Well, yeah, exactly, really exactly. And this is a good Q analog maker, let's put it this way. But this is not a right form. We have to introduce the compressed measure index. And here we need a second slide. So okay, so far we have the Doubloon. We locate the position of the descents in that of unfolding. And then we have the number of descents and the measure index, which is the sum of the positions of the descents. Now the compressed, very arbitrary. Why you define this? Well, we'll see in a moment where we have to make this definition. So for this, we call it the compressed with the mesh, okay, minus s plus 1 of the number of descents, and it's not quite positive, so we have to add something to make sure that it's positive. And if you add what you just do something you see at the end, and then it's okay.
Dominique, when you record the positions, you record the position based on the original word or in the folded?
Good point. Okay. Very good. Okay. Here you have the doubloon. You see doubloon. Then you have the positions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you follow row of delta. Follow row of delta. So let's examine here. It's the example we understand. It's the example of everything. So we have a descent in here. 9 is bigger than 8. So position 2. We have a descent at position 3. 8 is bigger than 6. We have a descent at position 4. No descent between 5 and 7. No descent. But the descent between 7 and 1. That's a descent. Right? And no more descent. So there are 4 descents. Okay. The mesh is 2 plus 3 plus 4 plus 6. 15. And to compress, you have the formula here. The mesh minus n as is 4 is minus 5 to the 4 times 4 plus n choose 2. N choose 2 is 4 choose 2 is 6. So it's, the compressed major is 1.
Is it equidistributed and natural?
Okay, and okay, now with the proposition coming on, I don't know, it's a weak theorem is coming. Okay, so that's an example. Maybe with this example, it's enough to understand the whole stuff. So let's repeat. We locate the positions of the descents. We number the descents. We add up the positions of descents, and with the compressed major index, which is the mesh, minus n plus 1, the number of descents, plus n choose 2. Oh, okay. So this is the table we had before. So we had for 2n plus 1, we calculate the C-mash. C-mash is 0. Well, we have to be quick, you know. The C-mash, the second one is 1. So accordingly, the Gini function for the C-mash on the all interlace will be 1 plus q. Here you remember we had 16. Here we are the interlaced. And here the other. The normalized, I'm sorry. Here are the pure interlaced. And if here I've computed the compressed major for all of them, then if you write what comes up, it's very simple. Here it's 1 plus q, here is 1 plus q, 1 plus q squared, 2 plus 2q. Fantastic. You have to prove it now, you see. So in other words, you have these polynomials factor out very nicely. And when when you plug q equal 1, look at this. It's 2 to the square times 4. Okay, so that's the right stuff. So first we have to prove, and we have to explain where it comes from. Okay. Now let's t 2n plus 1 of q. So this is the Gini function for the interlaced doublets by the compressed major. This is a Gini function for the normalized by the compressed major. And the theorem says that should extend this, we had before, the Durant proposition. So the Q proposition becomes a theorem, and that's t equal to this. Oh, then I'm sorry. This stands for